Hi all. In previous videos for Unit 3, one about the de Broglie wavelength, another about Heisenberg's uncertainty principle, we saw arguments that electrons have wave-like behavior. What we also saw was evidence when we looked at the diffraction pattern image made by a beam of electrons passing through slits. That was evidence that, again, electrons behave like waves. In this particular video, I will go over the basics of the Schrodinger equation, which takes Bohr's quantum theory and develops a new field called quantum mechanics. Another name for quantum mechanics is wave mechanics. Okay, how should we think about the Schrodinger equation? Let's look at an analogy. The Schrodinger equation quantifies the wave-like behavior of electrons and other subatomic particles. And it is a big part of the field of quantum mechanics. Which talks about what? The position and energy of subatomic particles. Position and energy of fast-moving subatomic particles like electrons. Very small particles. We could think of the Schrodinger equation as maybe the analogous to Newton's law of motion. And how laws of motions and how his laws described what? The movement, energy, and position of macroscopic objects that we can see. And that is the basis for classical mechanics. We talked briefly about quantum versus classical mechanics in a previous video. A bullet being shot, an apple falling from a tree, a train moving, and again, this describes the position and energy of macroscopic objects. Why don't I show you now at least one form, the simple form of the Schrodinger equation. I believe, oh boy, I really should have looked this up. I believe that the Schrodinger equation was developed in the early 1920s, or we'll just call it the 1920s. After Bohr gave his orbit theory or his quantum theory, right, of how electrons behave around a nucleus, next comes, or Schrodinger expands upon that. All right, I've delayed quite enough. The Schrodinger equation, I will never show the full equation or how to solve for numbers that help calculate the probability of finding an electron. That is way beyond this course of general chemistry. The simplest form of the Schrodinger looks like this. You have H, and sometimes it's a fancy H with a like serifs, and sometimes it has a little hat. Psi equals E psi. Now these are not, you're not multiplying. These are not multiplication operations. What H is, it's called a Hamiltonian. Whoops, Miltonian operator. And what is a Hamiltonian operator? It's a large set of mathematical operations. to be applied to a specific psi. That symbol right there. So psi is what's really important for us. Psi is called the wave function, and I'll do this in this color. Psi equals the wave function. Oops. And what is a wave function? A wave function is a description of electrons in a wave in 3 dimensions. This is a jump. It's a jump from Bohr's model, who said that electrons travel in orbits, basically flat orbits just like the planets. Here we're now going to think about where an electron can be in terms of volume, in terms of 3-dimensional shape. Now, on the other side, we have E, energy, and that is the energy associated with that specific wave function. There are many, many different wave functions, depending on what energy level the electron is in an atom. Okay, so this is the energy associated with that wave function. Don't worry, I will tell you what the most important parts of this equation is and what we can extract from it. But before I do that, let me show you more complicated forms or more expanded forms. I did a search on Google, and they could get pretty complicated. There are different wave functions, again, depending on what electron you're looking at in a specific atom. So here's one form. Again, we're not going to solve for the Schrodinger equation or even try to attempt to explain what each of these symbols mean. But here, it looks like they are considering energy and potential energy. There's another form, and it's here. So again, when someone says the Schrodinger equation, what the picture that I come up with is this one right here, understanding that these symbols carry within it large sets of operations and very complicated descriptions mathematically of the wave functions. But let me give you 3 things that you can take home, 3 take-home lessons. So number 1 is solving the wave function. Or should we say the wave function? Solving Schrodinger's equation. Gives the energy of and I'll put this in a different color. It's called an atomic orbital. So an atomic orbital. Okay, that I believe is a new term for us, and that is simply the volume where an electron can be found. The number varies. The most recent textbook that I saw, that shape of this orbital is the volume where an electron can be found 90% of the time. We can't know where an electron is 100% of the time, but we could have probabilities where if we have a volume, we could say 90% of the time that electron is going to be within that atomic orbital. Number 2, I put quotes here. Let me finish up the quotes there. Number 2, by squaring the wave function psi. The most important symbol in that Schrodinger equation is psi. And again, we should always know that as what? The wave function. By squaring the wave function psi, we get, very simply, psi squared. But what is psi squared? Psi squared equals the electron probability density. So that's the probability of finding an electron, okay, within within that volume. Don't worry, I have a couple of pictures that will make this hopefully a little bit more clear, but let me give you the third point that I want at least my students to remember. The total probability of finding an electron at some distance r, okay, r maybe for radius, is called, okay, out of these three, I want you to know what an atomic orbital is, and I want you to know what this probability, the total probability, it's called the radial probability density. Probability density, and I'll underline it, okay? Because we are going to see in later videos a more deeper consideration of this. Let me go now to another picture. I promised you a picture that will help you understand this idea of psi squared and where an electron can be found, in this case 90% of the time. And that picture is this picture right here. Okay, let's ignore the tree on the right for now. Okay, imagine this is a sphere. Okay. So the radius is projecting in all directions, and the middle is the nucleus, obviously. And what those dots represent is the probability of finding an electron in that position, in that location. You notice that it's more dense, right, towards the radius, or not towards the radius, closest to the nucleus. Now, if we do this graphically in 2 dimensions, you notice that you can never have really an electron right at the nucleus where the distance is 0. That's why it precipitously drops, right? But at some maximum distance from the nucleus, you will have a high chance of finding an electron. Okay. Again, imagine this not as a circle, but as a sphere. Okay, with most of the electrons, I shouldn't say most of the electrons, but the electron most likely being found closest to the nucleus, but not at the nucleus. And there it is, the sum of the psi squared. Okay, psi squared. Again, psi squared is what? The electron probability density. And what we're actually showing you here is now the radial probability distribution, or the radial probability density graphically. So you have a theoretical distance in which you can find the electron most of the time. This happens in real life, well, in real life, but also in things that we can see, in events that we can see, for instance, with this apple tree. Okay. Now, every now and then, okay, you'll get an apple outside of the 90% probability volume, okay? But This, I would say that this outer circle and anything within it, that represents that you'll find an apple 90% of the time. Now, the other 10% of the time, it could be outside of that volume. Okay, again, you got to think of this in 3 dimensions, not just a flat, uh, flat surface. So that curve looks very similar, right, to this curve here. We will do more with this in future videos. Probably the next video or the next 2 videos, we'll talk more about that. I just want to, this will be a shorter video. I just want to sum up. Yeah, I just want to sum up and give you more of a visual as to what I think, or what we should think of an orbital as. Just give me 1 second. Okay. You have your nucleus in the middle, and you have electrons, and your electrons are mostly closest to the nucleus, but they start to also spread out a little bit. Okay, but I'm trying to make it really dark in the middle. Okay, that represents, okay, 1 electron. Later on, we could think of it as 2 electrons because we talked about atomic orbitals. You could fit a maximum of 2 electrons in each atomic orbital. But ultimately, you could make a sphere that encompasses the volume where you could find an electron 90% of the time. So an electron in this is important, energy level. Because the shape of the orbital will change depending on the energy level and what's called the sublevel. And that, again, is the topic of either the next video or 2 videos from now. This is the atomic orbital. And it's just 1 atomic orbital. I do want to caution you. Oh, I didn't finish this thought. An electron in this energy level n, and we'll put n equals 1, can be found in the sphere. %90 of the time. A couple things. I purposely said n equals 1. Remember, this is from the Bohr's model, or Bohr's model, B-O-H-R model. Okay, we talked about this when n equals 1 or 2 or 3, and if an electron is excited, it goes to a higher energy level. And when an electron emits light, that means that the electron went from a higher energy level down to a lower energy level. The atomic orbital, when n equals 1, is spherical. But I do want to warn you, not all atomic orbitals are spherical. Okay. Hence, we will continue this discussion more on atomic orbitals and this idea of radial probability density in future videos. So, next 2 videos, we're going to talk more about atomic orbitals, okay, including what? The shape, the size, and connected to the atomic orbital, the radial probability density. Since not all atomic orbitals are spherical, the radial probability density, not all of them have that shape, where you have a peak fairly close to the radius and then it tapers off, right? This is r, or distance. Whoops, sorry, distance from the nucleus. And again, what was this axis? This axis was the sum of psi squared. So it's psi squared from the Schrodinger equation that we are most interested in. We will never put a number to this. Okay, what we will do is we will have the shapes described by psi squared for each of these different orbitals, these atomic orbitals that we are going to look at in the next two videos.